Alright, ladies and gentlemen, thank you for tuning in. This is Mr. Doolin, and today we're going to take a look at electromagnetic spectrum calculations. Alright, people, that's all I can do with that. I can't be that way. So here we go. We're going to jump right into it. I've got Bohr's model of an atom drawn there. It's not any particular atom. I'm just using it to diagram some electron excitation here. Hopefully by this lecture you understand the difference between a ground state atom, a ground state electron and a excited state electron. You know, a ground state electron exists in its normal energy level, and after it absorbs some energy, it can jump up into a excited state. All right, and then the drop back down actually releases some light. And so let's start taking a look at that and just really quick review. So I'm going to go ahead and make this electron blue. And so what happens is this electron can actually jump up. Now, when it gets up to the second energy level, remember it's excited, and we'll notate that with the little star. And now, I guess also you need to understand, I have to put energy. I have to put energy in to get this excitation to occur, right? Energy can be in the form of heat, light, chemical reaction can add the energy, motion. And so we've got energy going into our atoms. Our electrons get excited, they absorb that energy, and then when they fall back down, it's actually this drop back down, ladies and gentlemen, is the important part of this. That's when I get my photon emission. That's when my photon of light is actually released. It's when that electron falls back down. Now, some people have started to question, I'm looking at two different electrons here. Well, what if I put enough energy to actually get this guy to jump up into a higher energy level? Does that mean it has more energy? And the answer is yes. The distance that these electrons jump, right, and actually drop back down, it's really the falling back down to ground state. The amount of distance that they fall back down is proportional and directly proportional to the amount of energy contained within that photon. So, for example, if I'm going from an energy level 1, an n equals 1, to an n equals 3 jump, I'm jumping 2 energy levels there. What happens if this electron, as it falls back down, stops at the second energy level? And so I will release a photon of light, right? And then it will continue on and drop even further back down to its original ground state. And also in that one, in that second drop, I also get a photon released. So the question becomes, which one has more energy? Well, I think that's a little too complicated for this course, but definitely, if I'm going to go and show a third electron here, which in that particular case, let's just erase that one. I don't want you to think that there can be 3 electrons in the first energy level, because that can't happen. All right, so I'm going to jump up to that third energy level. There I am. I'm still in an excited state there, but now this time, what happens if I jump all the way back down? Right? I'm going to release that photon of light. And so now the question becomes, are these photons up here, or is this photon? Which is more energetic? Which contains more energy? And this one down here, this one would contain more energy. The drop was further. It dropped more energy levels. My light is going to contain more energy because my photon in itself has energy. And so now we keep on focusing energy, 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 energy. So how do we quantify this? All right, because this is about the calculations. How do we quantify it? Well, there's 3 different calculations we'll use. First, the speed of light, which is proportional to the wavelength of the light times the frequency, right? The speed of light is a constant value. C equals the speed of light. It is a constant. It is 3.00 times 10 to the 8th meters per second. All right, so the speed of light is constant. And so that's where we get our relationship. If wavelength goes up, frequency has to go down because it equals the same number every single time. The other thing, something when we start getting into relating this amount of energy, right? Energy is equal to Planck's constant times the frequency. So high frequencies equal high energies. And this H, which is equal to Planck's constant, right? These are 2 constants that you're going to have to know, is equal to 6.63, that's a point there, times 10 to the negative 34 joules times seconds. So that's joules times seconds over there. All right. So Planck's constant again, it just relates the proportionality of this frequency to this amount of energy, and this looks really similar to Einstein's, theory of relativity, the E equals mc squared. It's the same kind of stuff, right? So we understand that these photons, based on the frequency, they have an amount of energy, and that energy is proportional times Planck's constant to that energy, right? Well, there is a third one that we're going to want to know here. E equals hc divided by wavelength, right? There we go. Get off of here. Okay, there we are. And so with this, I'm using both constants, and I'm using my wavelength. What happens there is I just do that. That's a combination of both of those so that I don't have to convert wavelength to frequency all the time to actually determine energy, because since wavelength is proportional to frequency, it's also inversely proportional to energy there, all right? And so nothing crazy. This just uses both. Now, I do want to go back up here. I did forget to mention that my wavelength, those units are either going to be nanometers or meters. My frequency units will either be hertz, or you'll see it as 1 over seconds. They mean the same thing. And so we do want to carry through our units when we're doing our calculations. These are the three equations that you're going to be held accountable for, and this just goes back to your simple algebra. You're going to be given, in this one here, the first one, you'll be given 2 out of the 3 variables, solve for the third. In this one here, 2 out of the 3 variables, solve for the third. This one here, you'll be given 3 out of the 4, solve for the fourth one. It's not crazy. Don't overcomplicate it. These aren't crazy calculations, but they do allow us to start getting to what we want with how much energy is contained in this, because that's what chemistry is all about. Is we want to study matter, but we're more important, like we're really concerned with what kind of energy that matter has and what kind of energy changes occur as we change that matter. All right, so this is leading us into what everybody thinks of chemistry and the reactions and everything else. All right, okay, so if you had any questions, I hope you got them down. This is pretty straightforward. Come to tutorials to get those questions asked and answered. Ask them in class. We will make sure that you get an understanding so that we can move forward with this and start doing some of these quantifications. All right, I'll see you in class.